Welcome to the Cosmic Pi podcast. We're live streaming here from the beautiful campus at University of North Dakota. And because this is our first episode, we're going to do a little bit of a long introduction. So first of all, I am Wayne Barkhouse, and also hosting with me is...
Robert Moore.
So Robert, you want to tell us a little bit about yourself?
I certainly can. My name is Robert Moore. I'm the physics lab supervisor up here at the University of North Dakota, Department of Physics and Astrophysics. And for my background, I have a Bachelor of Science in Physics from the University of West Georgia, with a Master of Science in Astronomy from Georgia State University, and a Master of Science in Planetary Science from Case Western Reserve University. And I guess I could say that I'm interested mainly in planet formation, stellar formation, and variable stars. But I will talk about most topics. So I guess it's your turn.
Great, thank you, Robert. By the way, if any of you have any questions, please send us a live chat. We'll be answering them throughout the podcast, which lasts about approximately 1 hour. So my background is I have a bachelor's degree in physics from St. Mary's University in Halifax, Nova Scotia, which is on the east coast of Canada, and also a master's degree in astronomy from the same university. I also have a PhD from the Department of Astronomy and Astrophysics at the University of Toronto. After obtaining my PhD, I went on to the Harvard-Smithsonian Center for Astrophysics in Cambridge, Massachusetts to do a 3-year postdoc, and then on to the Department of Astronomy at the University of Illinois in Urbana-Champaign for 2 years. After that, I started a faculty position here at the University of North Dakota in 2007, and currently I am a tenured professor, full professor in the Department of Physics and Astrophysics here at UND. Now, the meaning or the purpose of this podcast is actually to have a conversation about various topics in astronomy, astrophysics, physics, and science in general. And so Robert and I are going to talk about various issues that are sort of on our mind today, so it'll be a real current events type of thing. But of course, we'd like to answer any questions that you have that we see in the live chat. So please submit questions as we go along. So first of all, I want to thank the University of North Dakota. I want to thank the College of Arts and Sciences and also the Department of Physics and Astrophysics here at UND that allow us to do this live stream and this podcast. So I'm going to turn things over first with Robert as we begin our discussions. Robert, do you have anything you'd like to talk about today?
I've got a few topics, but I'll start with the first one because I've seen a lot of news about it, and I've seen a lot of comments that make me realize people are misunderstanding what we mean of it in a few cases. And in this case, it's about there was a radio signal that is listed as now being the furthest signal away in radio wavelengths that has been detected. This was detected by the Long Meter radio telescope in India. And came to us from about 9 billion light years away. And the reason it caught my attention is because I saw a lot of comments to the effect of people thinking that this was a signal from aliens, we were saying. And the thing you've got to remember is that when we discuss signals, we're talking simply about, we've detected a radio signal. Folks, you give off radio waves, so you give off a radio signal, okay? So it's not necessarily a manufactured or something like that for there to be a radio signal. Anything that has a temperature above absolute zero is going to be broadcasting in radio waves. So this signal is coming from, basically it's the red-shifted signal for what we call the 21 centimeter of hydrogen. And this is a microwave signal that cold molecular hydrogen, so it's not incorporated into a star or into a hot gas body, gives off. So it's cold molecular hydrogen that we're detecting with this radio signal. And the importance of that is cold hydrogen gas collapses into stars. So detecting that signal gives us kind of a broadcast of where in this galaxy, or a picture, I should say, of where in this galaxy the cold hydrogen is, and therefore into stellar formation within these very early galaxies within the universe.
So, Robert, do you want to say something about how long after the beginning of the universe is this observation made?
I can make a comment on that because it's roughly 4 billion years after the birth of the universe. So while this is very young, we're not talking about what JWST is finding, where that's JWST is looking at galaxies that are a few 100 million years after. This is 4 billion. Big numbers, hard for us to understand, but basically JWST is looking 1,000 times further back than this radio signal came from.
Okay, so since you mentioned the JWST, we should note that that's kind of one of the most exciting sort of things that happen in astronomy, at least from infrared astronomy in the last 13 months or so, was the launch just over a year ago on Christmas Day on 2021 of the James Webb Space Telescope to great fanfare, and there's a good reason for that, of course. The telescope itself was well over budget. I think the total cost, the last I heard, was on the order of about $10 billion or so. And of course, it was delayed a lot. But, you know, if it takes going over budget, if it takes adding extra time to get it right, then it's worth it because it is an investment into the future. It not only does it allow us to look at things that otherwise would be invisible, to open up maybe new ways of thinking about the universe, but also it motivates young people to get involved in STEM fields, science, technology, engineering, and math. And so from that point of view, I think it's a well-done mission. Obviously, it's been very successful in terms of its deployment. And now really, from a science point of view, the fun is beginning. From an engineering point of view, I think most of the fun is probably over.
Most of the fun is done.
That was building the telescope and launching it and also get it to operate correctly in terms of its deployment, which was, you know, probably one of the most complicated things that we've ever done as human species in space itself. Now, some of the observations that's come from the James Webb Space Telescope have captured people's attention already. And one in particular we're going to show. Robert, if you want to bring up that image, see if we can do that. Away. It is a great distance away, but the interesting thing is that we can see individual galaxies within this cluster that are really, really far away. And you can see they're outlined in those small little squares that you can see there. They're numbered 1, 2, for example. And the redshifts, that's the Z value that you see there in sort of the middle panel. Those just reflect how far away these objects are. For the larger that Z value, the further away the object is. So these objects then, if you look at object number 2 in the bottom of that middle panel, which is also outlined in the panel on the far right, the small little square, you'll notice it has a Z value of about 12.5. So Z is known as redshift. So the universe is expanding. That's something we've known about since the 1920s. So, you know, nearly 100 years ago, that was discovered observationally. People had theorized that that was the case a few years before that, George Lemaitre and others. And so the redshift of 12.5 indicates that this galaxy, as what we're seeing here in the JWST image, is literally taken roughly 300 million years after the universe began. Now, the universe has a finite age. It hasn't been around forever. And we've shown that's the case many decades ago. The observational evidence for that is quite overwhelming. In fact, we can nail down the age of the universe today and know that it's approximately 13.8 billion years old. So the galaxy that we're seeing in the bottom of the middle panel, labeled 2 at redshift of 12.5, that galaxy formed roughly 300 million years after the Big Bang, after the formation of our universe. Now you might ask, what's the big deal? The big deal is just a few years back when people think about how galaxies form, and you could look at different processes from the point of view of physics, you can simulate it using advanced computer simulations. We thought that it would take on the order of hundreds and hundreds of millions of years for galaxies to form. A lot of estimate that I've seen tossed around was on the order of 1 billion years or so. But with the James Webb Space Telescope, we are seeing galaxies that existed before the normal formation time. They don't exist before the universe. I mean, you can't be older than your mother, for example. But the galaxies themselves formed quite rapidly in order to have the structure that we see that they have today. So what that really means is we have to rethink our formation of galaxies in this scenario, and it could be various ways of doing this, how we form galaxies, whether different types or another. Now, the interesting thing about this is that it does not say anything at all about the universe, about the Big Bang. The Big Bang model is not affected or challenged in any way, but certainly our ideas of galaxy formation are. Unfortunately, when people take this news and run away with it and try to get splashy headlines so that people will click on their stories or whatever, they don't quite have the full understanding that we need them to have in terms of science education. And we have this impression then that something's wrong with the Big Bang, that the JWST observations have ruled out the Big Bang theory, and so on and so forth. And that is not true. And that's one of these misconceptions that we have, and based on really not up to quality type of reporting. Now, I want to take this point to say something too. And that something is that the opinions expressed on this podcast are those opinions of Robert and I. They are not the opinions of the University of North Dakota necessarily. They are not necessarily the opinions of the College of Arts and Science here at UND, nor the Department of Physics and Astrophysics. So Robert, what do you think of this story, and what do you think about this whole sort of drummed up controversy in some sense?
I think, I don't know that I call it drummed up controversy, but it's definitely a matter of they try to sensationalize even science headlines, and it's because they need advertisers. That's how they make their money. So they want you to click on it so that you see the advertisements, so that advertisers want to advertise with them. But getting back to the science over the sociology and marketing of this whole issue, I'm going to say I draw a parallel with it on this issue with planet formation, because for the longest time we thought planets took 1 billion years after the star became a star to form. And when we started finding exoplanets and started finding disks, debris disks around young stars and so forth, what we found is that no, these debris disks are gone within 100 million years or so. So planets, if they form rapidly. And so to me, I'm kind of tickled, because what it means is galaxies form quickly too. And that's, to me, interesting. And it's interesting that, you've got this link between them. Is there it's correlation there? It's not any causation. You don't necessarily get one because of the same process as goes into the other. But I find it interesting that there is that similarity between the two.
Well, you bring up the idea of planets, Robert. So could you address the latest issue that I've seen that just appeared yesterday, the fact that a study came out that indicated that the core of the Earth has either slowed down tremendously or has actually stopped? And what effect would that have on, let's say, our environment, whether it's geological type of surface features or whether it's, the sea level and these sort of notions?
Okay. I can't speak too terribly in depth about this. I do know why they're saying this. It is, we can get seismic data, and the way sound waves or earthquake waves reflect and refract off of the inner core can tell us how it's turning, its size, and a lot of other information. And so that's how we know that that's going on, or how we imagine it's going on, because we're getting this signal back that it has to be because of this. We know how waves reflect and refract from the laboratory experiments. So what effect will that have? The only immediate or direct effect I can think of is it might have some effect on the magnetic field, because here's the deal, folks. The Earth is large. Roughly 6,000 meters radius. Trying to catch my thought here. So any deformation or change in the core, the inner core, has got to go be propagated through the outer core, which the inner core is only about 10% of the size of the total core. So it's got to propagate through comparatively a fairly sizable outer core. Then it's got to promulgate through a much larger mantle. That the mantle is like a big sand pile of little tiny grains. And so it's got to propagate through that and then through a very rigid layer at the very top. I don't think any distortion of the core is really going to produce much of a distortion in the surface. There are people speculating, oh, it will, but they're speculating. I'd have to see the science on that one.
So Robert, are you telling me the time I wasted watching the Core movie, it was all wrong?
Oh, the core. Oh, the
You
core.
mean we don't need to somehow get a nuclear bomb close to the core to
No,
restart
no.
its motion?
And I will go on record as saying that the same thing I tell students that bring up the movie The Core. We could take I've done a rough calculation of this, folks. We could take every nuclear device we have, take it down to the core, and blast it on the side of the core. And the core's reaction would be, something happened? Okay? The core is massive. And as big as we think a nuclear explosion is, a hurricane packs more of a wallop and has more energy incorporated into it than several nuclear weapons. So planetary scale energies are far in excess of anything we can produce for now.
For now. So you mean the notion that we've heard in growing up in the nuclear age in some sense is that we have enough weapons to destroy the Earth so many times over, and when people first hear that, they think, oh, do we crack the Earth somehow in half? But that's definitely not the case.
No. We have enough energy to wipe ourselves out, but the Earth is going to go, well, that was interesting, I guess.
So, Robert, do you have anything on your side for topics?
I've got a few other topics. Basically, I just thought maybe we'd get into some of the basics of astronomy. I will probably have several of these episodes where I'll talk some of these basics. So one of them is we use an unusual categorization scheme for stars. Unusual from the outside, anyway. That is, from most massive to least massive, the star categories go O, B, A, F, G, K, M. I got that right, didn't I? Yeah, O, B, A. Yeah, okay. So one, it's letters. Two, the letters are not in any kind of order, seemingly. And what happened is, oh shoot, now is when I needed the notes. The first person to categorize stars did so by their spectral hydrogen lines, how much hydrogen was in the star. And they assigned the ones with the most hydrogen the letter A, and the next most hydrogen B, C, D, E. And his scheme had 22 categories. Well, one of his assistants, a decade or two later, I think it was, Annie Jumpcannon, I do remember her name, simplified the scheme, and instead of tying it to hydrogen lines, tied it instead to the temperature of the star. So that gave us the current scheme of O, B, A, F, G, K, M, and it goes from hottest, and now we know most massive, to coolest and least massive with the M's. So from O to M, you're going from massive hot stars to low mass cool stars. That's the story of why we have that naming nomenclature, and each of those categories is broken down into 0 to 9. And so that's the story of it. And all I'll give extra on that is the mnemonic we use to remember the order of the stars. Please don't yell at us for this mnemonic, but it's O-B, a fine girl or guy, kiss me. So O-B-F-G-K-M.
Right, so that's the standard that you see in introductory astronomy textbooks for many decades. The other thing is, in recent times, because of very large surveys done by, for example, the 2-mass survey in the infrared, we've picked up a few more classification schemes on the cooler end. And so people are trying to get those to be officially part of that same sequence. So the hottest, as you mentioned, was the O-type stars. The coolest is the M-type. But we even find stars that are even cooler than M-class stars now, right until we get to objects that don't have enough mass to become a real star, which we call the brown dwarfs, of course.
Right.
And so at some point, it'll become officially adopted, I would assume, or everybody will gradually start to include that in their introductory astronomy textbooks, these additional classes for the cooler type stars.
And let me see if I remember right. Those are LT and Y?
Yes, I believe that's what it is. LT for sure.
Y, I'm pretty sure, are actually brown dwarfs, which, for reference, a brown dwarf is a body that is too low a mass to even begin deuterium, what we call deuterium or heavy hydrogen fusion. So they are in no way stars. And the only reason we even classify them in a stellar classification scheme, we call them brown dwarfs. They are really planets, except they're out there in the middle of space.
Right, and so the kind of thing I teach my intro astronomy students is that a brown dwarf would be an object that would have a mass less than about 8% of the sun's mass. The sun's mass would be an object that's like 2 times 10 to the 30 kilograms, if you can ever visualize what 10 to the 30 really means. Once we get into these very large numbers, in some sense it just becomes math at that point. You write it down, you can manipulate the equation and so on, but from a gut feeling, you know, what it really means to have something of anything of 10 to the 30 becomes sort of out of bounds. You know, I wouldn't mind having 10 to the 30 pennies in my bank account, for example.
Oh, Lord, yes.
But the other thing is, so these objects don't have enough mass. We sort of place them in a category between the lowest mass stars that are possible and the more massive planets that we find. And the interesting thing about planets, it really wasn't that long ago, just a little over 2 decades ago, where we didn't know of any other planets in the whole universe except those that happen to be in our own solar system. And at that point, any of the ideas of how those planets came to be, in terms of their formation and their evolution, was all based on a sample size of 1. Anytime you base anything on a sample size of 1, you end up into a lot of trouble, or can. And that's because you don't know how sort of characteristic that sample is to the norm. For example, if you happen to pick something that was completely different from 100 other objects, you just happened to randomly pick one that was completely different, you would make the assumption that that one object that you selected was on average the same as all the other objects that are in that sample, all 100 of them.
Looks like John Novak has a couple of questions. So go ahead, John.
So what happened then is that we started to find planets orbiting other stars. And really what we discovered is that most of the solar systems are not like our own solar system, they are different. And so we know the process of how solar systems came to be and so on and so forth, that is one of those things where there's a lot of different ways to put together a solar system. In fact, we've advanced to the point now where essentially, statistically, almost every star that we see in the sky has at least one or more planets. So that wasn't so clear a few years ago. And in fact, some people even speculate that maybe there are no other planets in our galaxy. That's an extreme, sort of a view to hold, of course. And maybe that's the case. We don't know until you do the observations. But today it is clear, for example, that at least statistically, there are probably several planets orbiting every star that we see in the nighttime sky. And if there are 200 to 400 billion stars in just our galaxy alone, the Milky Way, that means we're talking at least probably 1 trillion planets that are just in our galaxy. Yep. And there are at least 1 trillion other galaxies in the observable universe. And so there are a lot of planets then in our universe. And we always go down this rabbit hole of saying, what is the chance that life formed only on our planet, the Earth?
Right.
Where there's just so many planets out there. It's got to be somewhere else as well, one would think.
One would think.
The question, of course, is where is it? And how do we find it?
And I'm going to point out we got a couple of questions from John. The first one, oddly enough, is we ask ourselves the same thing. When are we going to get a clear night here in North Dakota? And the answer is, I don't know. I've been chomping at the bit the whole since November, wanting to get in some observing through the telescope that we have, and just can't do it because it's been cloudy the whole blessed time. In answer to number two, I will turn back to you because I don't even have a good answer on that one.
Yeah, so the question is, when will be the next observable supernova? The interesting thing about observable supernova, and here I'm going to take the assumption that we want a supernova that's viewable with the unaided eye. We don't need a telescope, we don't need binoculars. And the last observable supernova that went off in the Milky Way was about 400 years ago. Now, we can look at other galaxies and see supernova go off, and those require a telescope. And by studying other galaxies, we know that from a statistical point of view, we would expect that a supernova would go off roughly every 50 years or so. And there are a couple different main types of supernova, the core collapse supernova from massive stars, and also the supernova type 1a that come from white dwarfs that accumulate mass from a nearby companion star that's in orbit around themselves, a binary star system. And when that mass exceeds a certain limit, about 1.4 times the mass of our sun, called the Chandrasekhar limit, then that white dwarf will explode as this carbon detonation supernova. And so there hasn't been one in 400 years, and so we're well overdue. And why we know that is because supernovas should go off one every 50 years or so, then you can say, okay, well, we're expecting at least 10 supernovae should have been viewable since the early 1600s. But our galaxy contains a lot of interstellar matter, basically dust and gas. And what dust loves to do is absorb and scatter light. And if you have enough of this interstellar matter that's sort of in the way between us and some supernova that went off in our own galaxy, it can cause the brightness of the supernova to be dimmed to the point where we wouldn't even notice it unless you got very lucky and happened to look in a particular area with a telescope. And so chances are that we have missed statistically those supernovae that we expect to have gone off since the 1600s. So what we're really waiting for is a supernova that goes off nearby, and that would be bright enough that we could see with the unaided eye. Now, the last supernova that was visible to the unaided eye is the one that went off in the Large Magellanic Cloud back in 1987, supernova 1987A. That was the nearest, brightest supernova since the early 1600s. Unfortunately, from the northern hemisphere, that supernova was viewable in the southern hemisphere. You can't see the Large Magellanic Cloud from the latitude that we're located, for example, here in North Dakota. And so those people who lived or journeyed or traveled to the southern hemisphere at that time then would have been able to see the supernova in the nighttime sky with the unaided eye. And so we're still waiting. Now we can ask, of course, this question: which stars in the sky are most likely to go supernovae? And the ones we look for in particular would be the ones that are very massive near the end of their lives. Now, there are a few stars that fit that bill. Betelgeuse is one of them, or Betelgeuse, depending on how you want to pronounce it. So if we stick with Betelgeuse, this is the reddish star that we see in the constellation Orion. And I picked that star because as soon as it gets dark, if it is clear where you are located, if you look towards the south, you will see the constellation Orion this time of the year. And that star that's in the upper left top of the constellation, the shoulder of the constellation, that star is one of these on the target list that we keep an eye on to say it should go supernovae at some point. The problem is, when it goes supernova, will it be tonight? And if it does, it's just a coincidence. I don't have any cosmic sort of way of thinking of having the insight on these kind of things. But, we could be waiting for 10,000 years before it finally blows up as a supernova. And if it does, it's near enough to us that it will be extremely bright in the sky. Now, it could be very bright in the nighttime sky, or in the summertime, the constellation Orion, is actually in the daytime sky. So it actually would be bright enough that you would see it in the daytime sky. And so you could go out one day, for example, there would be the sun in some location, and you'd see the appearance of this new star somewhere else in that blue sky. In fact, these sort of things have happened in the past, and different cultures and societies on the Earth have recorded the presence of a new star. A very famous one happened way back in 1054, and that was responsible for creating what we call the Crab Nebula. So if you're into amateur astronomy or if you're an astronomer yourself, you'll know exactly what that is. It's just a leftover debris from the explosion of a star. And so those things have happened in the past and they will happen in the future. It's just whether or not it will happen in our lifetime. That's the big question. Yeah.
I cross my fingers because I got to admit that's for an astronomer, that would be one of the greatest things to witness is a supernova visible in the daytime sky. You don't need a telescope or anything. Just wow, that would be cool. Sorry, but that would be cool.
Yeah, and the other interesting aspect of that is because the supernova, if it's really nearby, we can do a lot of detailed studies of the supernova itself and therefore potentially find out a lot of things that we just don't know about today. For example, back in 1987, when the supernova went off in the Large Magellanic Cloud, the Hubble Space Telescope was due to be launched in the summer of 1986. So the Hubble Space Telescope would have been in orbit at the time that supernova went off. And when we say that the supernova went off, what we really mean is that the light from the explosion of that star, which is about 165,000 light years away, finally reached us. In terms of time, that explosion happened, like I said, 165,000 years ago. It's just that galaxy, the Large Magellanic Cloud, is so far away, it takes that amount of time for light to reach us from that location. And so, unfortunately, what happened, of course, if you know space history, is that the Challenger exploded in January of 1986. And because of that, when the supernova went off in 87, and just over a year later, the Hubble Space Telescope was not in orbit, which we thought it would be. It was actually in a warehouse in storage, waiting for the shuttle flights to resume, unfortunately. But NASA had other vehicles, other telescopes in orbit. One of them was the Ultraviolet Explorer Satellite, IUE satellite. And so that did a lot of sort of workhorse observations of the explosion of the star. Its telescope is sensitive to the ultraviolet, which means it likes to see very hot things. That was the purpose of the telescope, and clearly an exploding star is very hot. And one of the major things that we discovered from that supernova is that it actually originated from a blue supergiant, not a red supergiant. And we didn't know about that prior to that time, yeah. And because it was a blue supergiant, the explosion when it occurred did not reach as bright as it should have if it would have exploded as a red supergiant. And what happens is that for these massive stars, they actually, because they're very unstable, they actually get smaller and larger in size over a relatively short time scale. And they swing back and forth in terms of color, both to the red side and then to the blue side. And this massive star happened to blow up when it was on the blue side. And because it was smaller on average than what it would have been as a red supergiant star, it took more energy to cause the star to expand outwards in the explosion. And because of the use of this additional energy, it wasn't as bright when it reached its maximum point a few days after the explosion. So we learned something new just because that star was close and we could tell which star actually blew up, which is the progenitor, as we say. How do you know that? Easy. You take an image of the star field, which we happen to have beforehand, and then again look at it later on and you see which star is missing. Obviously, that's the star that blew up.
So, yeah.
Yeah, so
And we do a lot of that.
Right.
You know, when things blow up, or you get an anomalous signal. By that, I mean a signal that shows up and then goes away. You'll a lot of times go back to frames of that region and go, okay, let's look at what they were. Now let's look at what it is and see what's missing. And you do a lot of that.
So, Rob, do you have anything else you'd like to talk about?
The only other thing I really have that I planned on talking about is a little public service message, and that is about light pollution. Because just as detrimental to seeing things in the night sky as it being cloudy is honestly the amount of light we're producing outside. I know everybody likes to feel safe, and they feel safer when they can see things, but at the same time, we're washing out where, I got to admit, sitting in my apartment in town, I'm doing good if I can see and pick out Beetlejuice. So, It's time that we started taking into effect because, like, if you look at a map, and I should have brought an image, I'm sorry, I didn't anticipate things well enough. If you look at a satellite image of the U.S. At night, the East Coast, anything east of the Mississippi River, is pretty much just a wash of light, and it's pretty discouraging when you're wanting to look at the sky and look at the stars. And even out here in the West, there are very few places that show up as really being dark. There's a lot of glow, and there's so much that can be done to mitigate it. You can turn off some of the lights. It doesn't need to be like daylight outside at night. You can put hoods over the lights so that the light is downward where you want it anyway. And just things like this. You can have certain nights that you just turn off the lights. So, yeah, that's one of the things that I wanted to bring up and mention and say, let's start thinking about these things. And sometimes that's what we're trying to do with science is just get people to think.
One of the things you can think of when you're traveling by plane, let's say in the nighttime, you look down, you pass over to different cities, and you can see some of the lights, directly, right? It's like, well, why are they shining up in the sky? And we're eliminating, of course, the lights that are associated with the runway, right? To guide pilots to where to fly and land,
Right.
And so when you look at these lights that are shining upwards, and it could be from, different facilities on the ground, they're not illuminating anything on the earth. That light is wasted. That energy is wasted. So you're paying for wasted energy in that sense. So your electrical
Right.
bill is going to be higher than what it should be because some of that light is being broadcast straight up in the sky. Well, you don't need it up in the sky. And so why not have the proper shielding then on your lights that direct that light to go on the ground, which is probably where you want it. And therefore the light, you don't need to burn as much energy per hour to keep that light going to provide the illumination that you would expect.
Right.
The other thing is that light, even though you might think it just goes up in the sky and it's gone, it gets scattered around the atmosphere from the different particles that are in the sky, and it contributes to this overall sky brightness effect. For example, if you walk outside in the middle of Times Square in New York City and look up at the sky at night, what are you going to see besides the moon and a few bright stars? That is it.
Right.
And so if you're a young child that grew up, let's say, in New York City, you may not even feel an interest at all towards astronomy because you really didn't pay attention to the nighttime sky. It's not really on your radar, if you like.
It's orange.
Yeah. And so, when people do surveys and talk about, to different astronomers around the world, professional astronomers, and they ask them, well, where did you grow up? Well, most of them grew up in rural areas. That's because they were able to see the nighttime sky and actually be able to, become interested and develop a passion for the study of things that you see in the sky at night. And it's hard to do that when you're in a large city like that. Now, the other thing, too, that we worry about in terms of light pollution itself is that it's getting worse with time. So there was an article that came out recently, and the article said something to the effect is, as time goes on, we've noticed that people can see less and less and less stars. So the fainter stars are being washed out by the sky brightness. And that's just going to be more of an issue going forward in time unless we get smart about this. In fact, some countries, and I know Canada is heavily involved in this, they have different regions in the country where they call their sky preservation sites, night sky preservation sites. So there's areas designated to have dark skies. So you can't have bright lights nearby. And so people can go to these areas to do camping, to have a portable telescope, and so on and so forth. But it's a real shame that we have to be in that type of situation. Yep. That we have to designate these selected areas to have, to be relatively free of lights in the sky at night. That's unfortunate. Yep. And if you want to see the difference, just go from the city at night, go out into the rural areas to go camping, let's say in the summertime, and look up at the sky. And you go from looking at tens of stars to looking at thousands of stars, assuming you have normal vision, for example. And the difference is, should I say, astronomical? And for example, when you talk about, so we have a question about UND and about putting hoods over their lives, and that would be a great thing. And so if there's enough people that could ask UND to do that, especially if it saves money, Well, what a great thing. You save money at running the lights here on campus, and we save because we have astronomy outreach programs that we run at night. And we take people outside to look up at the night sky. And now it's becoming harder to find a place that's relatively free of direct light coming to you from some source. Now, there's a safety issue. I don't want a dark campus where students are walking around 11 or 12 o'clock at night. That can be dangerous. But of course, we need to have common sense in these type of rules to make sure that places where people normally would walk are illuminated, and other places that are not so, for example, in general fields or near the brook or these kind of places, that they would have less of the lighting around. So that would become more responsible for looking at the sky. In fact, the sky is not owned by anybody.
Right.
And so in that sense, any bright light that you have on, you're actually ruining my sky, right? You're trespassing on my ability to see, nature in that sense. So we have to get along, right? We're all sharing this planet. We're all sharing the same space. So we just have to be sensitive to others' issues on this sort of topic.
I've come up with the idea of not only could they place hoods on some of the lights, and we could then build a building specifically to put a telescope or an observation platform above the lights, so you could do that and see more of the stars. Still wouldn't be as good as a dark sky, but it would help. But another possibility is we got pretty good motion detectors nowadays. So you could put motion detectors on a lot of these lights, and somebody comes within 30 meters or so of the light, poof, it comes on, stays on for 15 minutes or after it stops detecting motion, and then it goes out again. And there are ways around this if we can just get people to get engaged in this conversation. And I think that's part of the problem. So I'm going to go with John Novak's suggestion. I don't know about calling up President Armacost, but
would he take our call, Robert?
I don't know that he would take our call. But definitely, if there's any kind of survey forms out there for facilities or anything like that, if you feel free to mention this, because it is an issue. It is a thing. So, yeah.
Right. The other thing I wanted to make sure we talk about before we end today's episode of the Cosmic Pie is actually to explain where the Cosmic Pie part of things come from. And when I'm teaching an intro astronomy class, one of the sort of first slides I like to show people is the Cosmic Pie. And the Cosmic Pie is just a breakdown of the composition of the universe in terms of all the matter and energy that the universe contains. And what it signifies basically is how little we do know of the universe. We always have this idea that astronomy in one form or another has been around for literally tens of thousands of years, ever since human beings had the curiosity to look up at the night sky, for example, and wonder what all those little lights are, or to look up at the sun during the daytime or the moon, and a sense of wonder of where does it come from, what does it mean, all of these sort of things. And so astronomy's been around, and one would argue from a scientific point of view, at least it's the time of Galileo. Okay, you could say that with the use of the telescope to look at the sky in the early 1600s, that we somehow know everything. So why should I, as a student that is looking towards it in a career in the science, let's say, would forego looking at astronomy as a serious profession because we know everything. We've been studying for 400 years. What's left to be discovered, for example? And the Cosmic Pie illustrates the point when you look at the breakdown of everything that's in our universe. For example, the stuff that you and I are made of, the stuff that this desk in front of us is made of, the screen behind us, the building that we're in, and so on, the planet that we're standing on, all of that is made up of things that we'll call it normal matter. Okay? And that would consist of things like protons, neutrons, electrons, and so on, those sort of things. That turns out to represent only 5% of the whole universe, 5%, which clearly that leaves 95% that is not made up of ordinary matter. So what is that other 95% all about? Well, first of all, approximately 25% is made up of something that we call dark matter. And we can get into dark matter, if not today, in the future podcasts, and explain the ideals of what dark matter is all about and what we think it is and so on. But, it's safe to say that today, we do not know what the dark matter is. Nobody could stand on a soapbox and say, I claim to know what dark matter is, here's what it is, give me that Nobel Prize and I'll go spend the money type of thing, right? That's not going to happen today. So that represents 25% of the universe. The other section that's left, the last slice and the largest slice of the cosmic pie, is something that we call dark energy. So this 75% of the universe, this was discovered in 1998. And what we discovered was not only is the universe expanding, but that expansion is accelerating. It's picking up speed, if you like. It's expanding at an ever greater rate as time marches forward. Now, that was not expected. From an observational point of view, it made the universe in some sense more complicated than what it was prior to that. What people had thought was that as time marched forward, the universe, which is expanding, it's something that people observed in the 1920s, we thought that expansion rate would slow down. And why it would slow down is because of the combined gravitational pull of everything that the universe contains, all of the matter, all of the energy. Okay? And so therefore we'd expected the expansion rate to slow down with time. And it was just a matter of trying to observe precisely as possible how much is the universe slowing down by. We call that the deceleration parameter, if you want to think of some technical terms about that. And what we discovered instead is it's not slowing down the expansion rate, it's actually speeding up. So we don't know what causes that to occur. That's the ultimate sort of conclusion today. We coined a term for that. Michael Turner from the University of Chicago, he called it dark energy. So it kind of fits nicely with the dark matter term. So we use the term dark energy, but we don't really know what causes dark energy. We can describe its effect, the accelerated expansion of the universe, but we don't know where it comes from. There's a lot of speculation, of course, but we have to figure out ways to try to understand better what it's all about. But if you take the dark energy slice of the universe and you take the dark matter piece, add those together, 70 plus 25, that's 95% of the universe we just don't understand at a fundamental level.
Don't have a clue.
We only understand that 5%. And by the way, if you're a chemist, that's the part you deal with, that very tiny slice of the pie, that 5%. You don't deal with the dark matter slice, and you certainly don't deal with the dark energy slice. So to say that we somehow know everything in astronomy and what's left to do is dot the I's, as they say, and cross the T's, is totally wrong. We have this 95% that we need to figure out at some point. And it may be 10 years from now, it may be 1,000 years from now before we figure this all out. We just don't know. That's the excitement with science. You don't know where the next major discovery will occur and when it will happen.
So get out there, learn the science, and win your Nobel Prize. That's my statement, you know.
In other words, become rich and famous?
I don't know about that, but you know, I don't know how famous Nobel Prize winners are. I mean, how many can the average person name? You and I are not average people. You know, but you know, I'm in favor of, and I tell students all the time, you know, we don't know the answer to that. Go win your Nobel Prize,
Right.
and I mean that. And Upland Emu, I'm going to say I have no idea if we'd be able to get President Armacost on the podcast. The answer is probably not.
Well, I don't know if we can get anyone on the podcast.
This being our first episode, we don't know.
Yeah, we don't know how long we're going to be here. They might go on there once and they'll say that's enough. No more.
That's enough. You two did enough damage.
Remember, the opinions expressed on this podcast are ours, not the university's. Now,
Lordy.
the other thing, too, I want to mention, Robert, is the fact that, you know, lately, if you study cosmology, which is the study of, you know, the origin, the evolution, and if you like, the future of our universe, if you study cosmology, there's been this issue that's been bubbling around for a few years now, since we've talked about the expansion of the universe, is to try to figure out what exactly is the expansion rate. What is that value?
Right.
Okay. In fact, that was one of the driving forces behind building the Hubble Space Telescope back in the 1970s, was that one of the key projects was to try to get a better handle on what we called then the Hubble constant, the expansion rate of the universe. Nowadays, we actually call it the Hubble-Lemaitre parameter or the Hubble-Lemaitre constant, just to bring in the fact that George Lemaitre, who was a Catholic priest, actually did a lot of theoretical work prior to the discovery from an observational point of view by Edwin Hubble and others, that the universe was in a state of expansion. And so we like to honor both people at this point in time. Now, what is that expansion rate? Well, from the Hubble Key project, the expansion rate was on the order of roughly 70 kilometers per second for every what we call 1 megaparsec of space. Now, I use the term megaparsec, that's something you might hear on Star Trek or something like that, right? So a parsec, it really comes from the word parallax second. And what it means is, for example, if you wanted to determine from a surveying point of view the distance to some remote object, let's say that you're a surveyor and you're out surveying an area around a large lake. And the lake is large enough that the object you want to look at, let's say, is a house that's on one side of the lake and you happen to be on the other. And there's no real good way of getting on the other side. It would take a lot of time. Maybe there's a river that's running into the lake on one end and another river that's running out at the other, and you can't traverse the river. You don't have the ability to do it at that point in time. So one way to get around that is you can look at the position of the house relative to the background, and then move your point of observation a little further away and look at that same house relative to the background. It's a little like putting your finger in front of your nose and looking at it with one eye against the background and then looking at it with the other. And if you go back and forth, you can see your finger shifting back and forth as you observe from them first one eye and then from the other eye. So you change your location of observation. That's known as parallax. Now that shift in position of your finger or the house, if you're looking across a lake, that's related to two things. The separation point of your two observations, so in other words, the distance from one eye to the other eye in the case of the finger, and also how far away that object is. How far away is that house from where you're making your observation from? Well, we can use that to also measure the distances to objects in space. We can use that to measure the distances to nearby stars, for example. And by doing that, you're going to say something?
I was just going to point out, make note that this is by using geometry. Okay, so people often question how we really know how far away things are. Well, this method is geometry, so either geometry works or it only works here. I'll let you be the judge on that. Which statement makes more sense?
Right, and so we can use that to basically build up a distance scale of looking at how far away objects are. And eventually we can get to the point where we can measure that fact that if an object happens to be at a certain distance away, it will display a shift in angle. It's actually 1/2 of the total angle that's equal to what we call 1 arc second. And the distance that a star would have to be to display an angle of 1 arc second, assuming we're viewing it from one side of the Earth's orbit to the other side of the Earth's orbit, that would be a separation distance of twice the distance from us to the sun, which what we call in astronomy 2 astronomical units, for example, where 1 astronomical unit is the average distance of the Earth to the sun. If that shift is 1 arc second, the distance to that star would be 3.26 light years, approximately. And that's the 3.26 light years is the distance that light travels in 3.26 years. It's roughly 9 trillion kilometers a year, or 6.5 trillion miles, sort of roughly on average. And so the idea was that we call that distance then of 3.26 light years 1 parsec. So in cosmology, we're dealing with much larger distances than that. So we're talking millions of parsecs. So the Hubble's constant then was measured to be roughly 70 kilometers per second per megaparsec. That means for every 1 megaparsec length of space. So imagine space of 1 megaparsec is this long. This is extragalactic space. That space is getting larger by 70 kilometers as every second goes by on the cosmic clock. That's the expansion rate currently. Okay. So there are different methods that we can use to measure that expansion rate. And some of those methods, after studying for several years now, we can nail down the uncertainties. So we can make these observations, these measurements, more and more precise. Okay? Now, we don't know anything about accuracy, of course, because we don't know what the true value is of the Hubble constant. That's something we're trying to measure. The interesting thing that happened a few years back is we made a measurement of the expansion rate of the universe based on observation of the leftover heat from the Big Bang, what we call the cosmic microwave background. Now, if you think of the universe as in a state of expansion, then clearly if you go back in time, the universe must have been smaller. And as you take a certain amount of material, let's say gas, and if you squeezed it down into a smaller and smaller volume in a smaller can, for example, or a container, one of the things you'll notice, of course, is that the density goes up. This density is defined as mass divided by volume. If the volume gets smaller, the density has to go up. But also the temperature rises. So as we go back in time towards the early beginning of the universe, the temperature of the universe in that sense should increase. Now, going forward in time, as the universe continued to expand, that temperature dropped. If you like, you can think of it as the heat from the leftover heat from the Big Bang filling up an ever larger volume of space. So the temperature cools down, the temperature drops. Now, by measuring that leftover heat from the Big Bang, even though it's extremely cold today, very cold, even way colder than January in Grand Forks.
Or even Siberia.
Yeah, so from that measurement of that leftover heat, you can measure roughly the expansion rate of the universe. And we come up with a certain value. It's on the order of roughly 67 kilometers per second per megaparsec. But when we compare that to other techniques that people use to measure the expansion rate, we find that those techniques which are usually based on more local things, the cosmic microwave background by its definition is a really global or universal type of measurement. When we compare that to other techniques that are done locally, we find that the expansion rate is a bit higher. In fact, it is a bit higher, but high enough that there is a huge difference between the two in terms of the uncertainties. They're what we in science we call more than 5 sigma different from each other. Okay. Now, that's called the Hubble tension today, as we say. Why does one measurement, based on very large scales, give you a lower measurement to the expansion rate based on things that occur more locally? And there are a lot of cosmologists, a lot of scientists that are sort of working in this area today, trying to figure out why there is this difference. It could be based on several things. We don't know what the answer is right now. Number one is we don't really have a good understanding of the total uncertainty in these techniques. Maybe we're missing something. In science, we would say maybe we're missing some type of systematic bias that we're unaware of. And if we included that, the uncertainties get a bit larger to the point where they overlap significantly these two values, that they're not statistically significantly different from each other. We just don't know. Or another possibility is that the universe itself has a lot of structure associated with it. That is, galaxies are not spread randomly throughout the universe. There's something that we call the cosmic web, what we call the large-scale structure to the universe. In fact, we live near a relatively empty region or a low-density region in that cosmic web, what we call a void. So we're sort of on the edge of a void. Now, does that have an effect on these local measurement of the Hubble constant? Where if you compared it to the one done by observing the leftover heat from the Big Bang, that would be averaged over a huge number of voids, essentially all of the large-scale structure in the observable universe. And so any effect by being near a void or away from a void would get washed out in those type of measurements. Maybe that's what's happening, but at this point in time, we don't know. In fact, some people suggest that this is, other than dark energy and dark matter, that this is, the third most important question that we need to answer in terms of cosmology itself.
Yep. And that's about our time.
Yeah, it looks like we're near the end of the first podcast. Boy, did that go.
John Novak, that's a detailed question that you've just asked about the density and whether or not there's hypothesis. There's a difference between a theory and a hypothesis. That the new universe could be in a singularity of a black hole. And I think we're going to have to save that topic for another day. I'm sorry to put you off, but yeah, we're kind of out of time.
Actually, that would be a good topic to discuss black holes on the next podcast.
Works for me.
Yeah,
so tune in
we'll
next time, John. We'll get to you. We
Right.
promise.
So once again, I just want to thank the University of North Dakota, the College of Arts and Sciences, and also the Department of Physics and Astrophysics to allow us to do this podcast. Our next podcast will be next Tuesday, January 31st, beginning at 3 p.m. Central Time. And for the time being, I'd like to leave you with a quote. And the quote is, "The beginning of wisdom is not to know all the answers, but to realize the questions to ask." Thank you for listening.
Thank you all.